Some of the most violent events in the cosmos leave no light behind at all. When two black holes spiral together and merge, or two neutron stars collide, they announce themselves not in photons but in a trembling of spacetime itself, a gravitational wave, a ripple in the very geometry that governs distance and time, racing outward at the speed of light. Einstein predicted these waves in 1916, but for a century they seemed forever beyond reach, because spacetime is fantastically stiff, and even the most cataclysmic merger stretches the space here at Earth by only about 1 part in a billion trillion. This chapter follows the physics of gravitational waves from Einstein's equations to their first capture in 2015, and on to the founding of an entirely new kind of astronomy, one that listens to the universe as well as looking at it. The concept follows directly from general relativity, in which gravity is not a force but the curvature of a four-dimensional spacetime, shaped by mass and energy. In 1916, and more definitively in 1918, Einstein showed that the weak field equations admit wave-like solutions that travel at the speed of light, carrying energy away from their source. A crucial feature sets gravitational radiation apart from the electromagnetic kind. Electric charge comes in two signs, so the simplest radiating configuration is an oscillating dipole, but mass comes in only one sign, and a center of mass cannot accelerate on its own, so no gravitational dipole can radiate. The lowest configuration that can is the mass quadrupole, a measure of how non-spherically the mass is arranged. A perfectly spherical collapse emits nothing at all. A spinning dumbbell or an eccentric binary radiates copiously. The wave that results is transverse with two polarizations, and as it passes through a ring of free masses, it stretches the ring one way while squeezing the other, then reverses the quadrupolar breathing pattern that detectors are built to feel. The road from prediction to detection took a century, and it was conceptually fraught, not merely difficult. Einstein himself wavered. In 1936, he drafted a paper concluding the waves did not exist, before a referee showed that his apparent problem was an artifact of the coordinates. Whether the waves were physically real, whether they carried extractable energy or were a mathematical illusion, was settled only in 1957, when Richard Feynman offered his sticky bead argument, showing that a passing wave would slide beads along a rod and do real work upon them. The first experimental hunt, Joseph Weber's resonant aluminium bars in the 1960s, produced claimed detections that no one else could reproduce, but it galvanized the field and inspired the interferometric approach that Rainer Weiss, Ronald Drever, Kip Thorne and others would build into the vast machines of the LIGO project. The decisive early vindication, though, came not from any laboratory, but from a pair of stars in the sky. The engine of the theory is the quadrupole formula, derived by Einstein in 1918, which gives the power a system radiates in gravitational waves in terms of the changing shape of its mass distribution. Its profactor is staggeringly small, so only truly enormous, rapidly changing masses radiate appreciably, and a binary of two compact stars in a tight orbit is the ideal source. Peters and Matthews worked out the details in the 1960s. Because the waves drain energy from the orbit, the two bodies spiral inward, the separation shrinks, and paradoxically, the orbit speeds up as it decays. An isolated binary will therefore coalesce in a finite calculable time, sweeping through faster and faster orbits until it merges. It is this inexorable, precisely predictable inspiral that makes the merging compact binary the workhorse source of gravitational wave astronomy. The single quantity that governs the inspiral is a particular combination of the two masses called the chirp mass. As the binary tightens, the gravitational wave frequency climbs in a way that depends only on this chirp mass and on measurable quantities, so that by tracking the rising frequency alone one can read off the chirp mass directly, with no need to know how far away the source lies, a property that will matter greatly later. The name is apt. The signal is literally a chirp, a tone that rises in pitch and swells in amplitude as the merger approaches. For the first event ever detected, the chirp mass worked out to about 28 solar masses. In the final moments when the two bodies are whirling at a good fraction of the speed of light, the neat approximations break down, and only a full computer solution of Einstein's equations, numerical relativity, first achieved stably in 2005, can model the violent merger and the ringing that follows. Gravitational wave sources span an immense range of frequencies, and they fall into four broad classes. Compact binary coalescences, merging black holes and neutron stars, are the only kind detected so far by ground-based instruments, and they produce the canonical chirp, a rising inspiral, a violent merger, and a brief ringdown as the remnant settles. Continuous waves are the faint, near-perfect tones expected from a spinning neutron star with a tiny mountain on its crust, as yet undetected. Stochastic backgrounds are the blended hum of countless unresolved sources, possibly including a relic from the very early universe. And bursts are short, unmodelled flashes, a collapsing star or something never seen before. The frequency of a source is set by its density, so the compactness of the emitter fixes its band. From the kilohertz cries of stellar mergers down to the nanohertz murmur of the largest black holes, the sources together span some 12 decades of frequency, the gravitational wave analogue of the electromagnetic spectrum. To feel a strain of 1 part in a billion trillion across a 4-kilometre arm means measuring a length change of about a 10,000th of the width of a single proton. The instrument that achieves this is a giant Michelson interferometer. A laser beam is split in two and sent down 2 perpendicular arms, kilometers long. Mirrors reflect the beams back, and they recombine at the splitter, tuned so that in quiet times they cancel and no light reaches the detector. A passing wave lengthens one arm while shortening the other, unbalancing the interference and spilling a trace of light onto the photodetector. And it is the difference between the arms, not their common motion, that carries the signal, which is why the L-shape is ideal to magnify the effect. Each arm is a resonant cavity in which the light bounces hundreds of times before leaving. 2 such observatories make up LIGO in Washington and Louisiana. Virgo stands near Pisa, and KAGRA is buried in a Japanese mine. The whole art lies in defeating noise. At the lowest frequencies, the ground itself trembles, and the mirrors, 40-kilogram cylinders of fused silica, must be hung on delicate multi-stage pendulums to isolate them from the shaking Earth. Below a few hertz even, the shifting gravitational pull of passing seismic waves becomes an impassable wall. In the middle band, the random thermal jitter of the mirror surfaces sets the limit, which is why KAGRA cools its sapphire mirrors to 20 degrees above absolute zero, and why it was built deep underground. And across the whole range there is quantum noise, the irreducible flicker of the vacuum itself, the graininess of light. Even this is now being beaten by injecting specially prepared squeezed light that shifts the quantum uncertainty out of the measured quantity, enlarging the volume of the universe the detectors can survey. Because a single L-shaped detector is nearly blind to direction, a global network is essential. The tiny differences in a wave's arrival time between widely separated detectors triangulate its place in the sky. A gravitational wave signal does not arrive standing proudly above the noise. It arrives buried far beneath it, the chirp entirely invisible to the eye in a stream of featureless static. It is dug out by a technique called matched filtering, the optimal way to find a known shape, hidden in random noise. The data are cross-correlated against a vast bank of theoretical waveforms, each computed for a different set of masses and spins, and weighted so that the frequencies where the detector is quietest count for most. When a template matches the true signal, the correlation rings out. The first event was recovered this way with a confidence corresponding to less than 1 false alarm in 200,000 years. Once a candidate is found, its properties are estimated in a framework that explores a 15-dimensional space of possibilities. The masses, the spins, the distance, the position, and the orientation, returning not single numbers but full probability distributions, complete with their characteristic degeneracies. Long before any wave was caught directly, the reality of gravitational radiation was established by watching a distant orbit slowly decay. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar locked in a tight 8-hour orbit with another neutron star. A pulsar is an exquisitely precise natural clock, and by timing its pulses over years, the 2 astronomers watched the orbit shrink, exactly as it must if the system were bleeding energy into gravitational waves. The measured rate of decay matched Einstein's prediction to better than 1/5%, the first decisive proof, if an indirect one, that gravitational waves are real and carry energy away, and the achievement that won Hulse and Taylor the Nobel Prize in 1993. That same binary was also the archetype of a system destined, in a distant future, to spiral all the way in and merge. That kind of merger was finally caught on the 14th of September, 2015. The 2 advanced LIGO detectors, newly upgraded, registered a signal that swept upward from about 35 to 250 Hz in a fifth of a second, the unmistakable chirp of two black holes, of about 36 and 29 solar masses, spiraling together and merging into a single black hole of some 62. The three missing solar masses had been converted entirely into the energy of gravitational waves. For a few thousandths of a second, the merger shone in gravitational waves more brightly than all the stars in the observable universe combined. The waves had travelled for some 1.3 billion years to reach us. Announced in February 2016, the detection was a triple triumph of gravitational waves, of black holes as real objects, and of Einstein's theory in its most violent regime. And it brought Weiss, Barish and Thorne the Nobel Prize in 2017. The merger does not end the signal. The newborn black hole rings like a struck bell, shuddering in a set of dying tones as it settles. Remarkably, the theory says a black hole is described entirely by its mass and its spin, so those ringing frequencies are fixed by just those two numbers. And checking that the ringdown agrees with the mass's read from the earlier inspiral is a direct test of that no-hair principle which the data have so far passed, and where there was one event there are now hundreds. As the detectors grew more sensitive across successive observing runs, the trickle became a flood. The latest catalogue, released in 2025, brought the tally of confident detections past 200. What were once rare curiosities are now a statistically characterized population of compact objects, mapping out the masses, the spins, and the merger rate of black holes across cosmic time. Some individual events have overturned settled expectations. In 2019, one merger combined black holes of about 85 and 66 solar masses into a remnant of roughly 140. The first clear case of an intermediate mass black hole formed by merger. Its heavier component fell squarely in a forbidden range of mass, where ordinary stellar collapse should leave no black hole at all, pointing instead to a black hole built from earlier mergers in a dense star cluster. Another event that same year paired a black hole with a compact object of just 2.5 solar masses, sitting in the mysterious gap between the heaviest known neutron stars and the lightest known black holes, leaving its very nature undetermined to this day. Each such oddity is a probe of how these binaries form, and of the strange demographics of the compact objects the universe makes. When the merging bodies are neutron stars rather than black holes, something new becomes possible because neutron stars are made of matter, and a merger flings a portion of that matter out into space. Neutron stars are the collapsed cores of once massive stars, city-sized balls so dense that a sugar cube of their material would weigh as much as a mountain, made of the most neutron-rich matter in the universe. When two of them collide, tides and shockwaves tear loose perhaps a few hundredths of a solar mass of this material and hurl it outward at 1/10 of the speed of light. In that expanding cloud of liberated neutrons, one of nature's great acts of creation takes place, the forging of the heaviest elements in existence. The process is called rapid neutron capture, and it answers one of the oldest questions in astrophysics. Where do the heavy elements come from? About half of all the elements heavier than iron, the silver and the gold, the platinum, the uranium, are built when atomic nuclei swallow free neutrons faster than they can decay, climbing to ever heavier and more neutron-rich forms before settling back toward stability. A neutron-star merger supplies exactly the explosive, neutron-drenched conditions this demands. The freshly minted nuclei are radioactive, and their decay heats the expanding debris until it glows, a transient called a kilonova, 1,000 times brighter than an ordinary nova. Its color betrays its contents. Cloak the ejector in heavy rare earth elements and it shines slow and deep red. Leave them out and it flares briefly blue. In the gold of a wedding ring and the platinum of a catalytic converter, we are wearing the debris of ancient collisions between dead stars. All of this passed from theory to observation on the 17th of August, 2017. That day the LIGO and Virgo detectors recorded a gravitational wave signal a full 100 seconds long, far longer than any black hole chirp, because the light neutron star masses linger in the detector's band, from a source just 40 megaparsecs away. And a mere 1 3/4 seconds after the waves peaked, two orbiting gamma-ray telescopes caught a short burst of gamma rays from the same patch of sky. 11 hours later, optical telescopes in Chile pinpointed a new point of light in a galaxy called NGC 4993. Over the following days and weeks, some 70 observatories, spanning every band from radio to gamma rays, watched the glow fade from blue to red exactly, as kilonova models had foretold. A single event was being read simultaneously in gravitational waves and across the whole electromagnetic spectrum. The scientific harvest of that one event was staggering. The coincident gamma-ray burst confirmed a decades-old hypothesis that merging neutron stars are the engines of short gamma-ray bursts. The fading kilonova, its spectrum revealing freshly made strontium among the debris, delivered the first direct proof that mergers really do forge the heavy elements, no longer an inference but a citing of the factory in the very act of production. Here was the long-sought answer to where the universe's gold is made, written in the light of a single collision 40 megaparsecs away. The event has become the founding moment of a new discipline, multi-messenger astronomy, in which one cosmic happening is observed through more than one of nature's fundamental channels at once. Two further measurements from that merger reached down to the foundations of physics. The gamma rays arrived less than 2 seconds after the gravitational waves, having raced neck and neck across 40 megaparsecs, pinning the speed of gravity to the speed of light to within about 1 part in 1,000 trillion, and wiping out whole families of rival gravity theories at a stroke. And because the amplitude of a gravitational wave encodes the absolute distance to its source while the host galaxy supplied a redshift, the event yielded a wholly new measurement of the expansion rate of the universe, a standard-siren, calibrated by gravity alone, owing nothing to the traditional ladder of cosmic distances. The subtle tidal distortion of each neutron star, imprinted on the final moments of the signal, even constrained how matter behaves at the crushing densities of a stellar core, favoring neutron stars about 12 kilometers across. Gravitational waves are only one of 4 messengers now carrying news of the cosmos, alongside light, cosmic rays and neutrinos, and the ghostly neutrino was in fact the first to herald a distant event, when a couple of dozen of them arrived from a supernova in 1987, hours ahead of its light. Today, at the far opposite end of the frequency scale, astronomers have turned the galaxy itself into a detector. Scattered across the Milky Way are millisecond pulsars, the most stable natural clocks known, and a gravitational wave with a period of years will subtly advance and delay their ticks. By timing an array of these pulsars for years and hunting for a characteristic pattern of correlations across the sky, astronomers can sense the slow, nanohertz hum of the universe's largest black hole pairs. In 2023, several such teams announced the first evidence of exactly this background, the collective murmur of supermassive black holes, millions to billions of times the mass of the Sun, orbiting at the hearts of merged galaxies. The future of the field is already being built. On the ground, next-generation observatories, Europe's Einstein telescope and the American Cosmic Explorer, with arms of 10 and 40 kilometers, are being designed to hear mergers across almost the whole of cosmic history, but the most dramatic step is into space. In 2024, the European Space Agency formally adopted LISA, 3 spacecraft flying in a triangle 2.5 million kilometers on a side, trailing the Earth around the Sun and trading laser beams to sense ripples in a band far below anything reachable from the shaking ground. Launching in the 2030s, LISA will hear the mergers of giant black holes clear across the universe, track thousands of compact binaries in our own galaxy, and even catch stellar mass binaries years before they cross into LIGO band, opening a whole new window, and the prospect of following a single source from one detector to another as it spirals to its end. For all its youth, gravitational-wave astronomy already presses on the deepest open questions. Foremost among them is the Hubble tension, the stubborn disagreement between 2 ways of measuring how fast the universe expands, one anchored in the nearby cosmos and one in the light of the infant universe, which now differ at around the 5 sigma level. Whether it signals a crack in our cosmology or a hidden error, no one yet knows, but the standard sirens offer a wholly independent referee, and a few dozen well-located mergers could settle the matter. Other questions crowd behind it: the true behavior of matter inside a neutron star, the ways compact binaries are born, the possibility of black holes left over from the Big Bang. Barely a decade after the first detection, a sense hangs over the field that it has heard only the opening notes, and that the gravitational wave sky in time will grow as detailed and as full of surprises as the sky of light has been for 400 years.